Anything else before we get started? I do regret dropping new lecture material on you guys the day of the test. This will not be covered on the test. We're going to save this for later. And the amounts to be determined later. I want to share this one. And then record, which we are doing, and then start. Okay. So this is taking us back to, I want to pick up where we left off in our parent material slides. We talked about lithosequence. This is the comparison across different parent materials. Got it. That looks good. And the way you recognize a change of parent material is really any change in the color, texture, structure, or coarse fragments to the rocks that you can describe in a profile are going to be a big indicator of the parent material that we have. So just like yesterday, we're talking about a big loss event. Like we can imagine that happening many times. It's blowing up dust, kicking up dust around, not really kicking up rocks though. So the hazards in a dust storm like that are like trees falling over, right? Not necessarily good sized rocks being thrown by the wind. So
there's also hazards of just the low visibility.
Yes. When we're talking about soil formation, however, we're not going to consider rocks in like a loess parent material. So if you have something smooth, silty, might be less parent material, but then like in the top half of the profile, then in the bottom half, you all of a sudden you find really jagged, coarse rocks. Chances are you have a change in the parent material. Something had to change in the geologic formation for that would specifically be like texture or coarse fragment change. Yes, but it really starts to tell the story of the soil profile, like I was talking about with paramaterials. The idea that soils tell a story is really, if I had to boil it down, what I love most about soil science in the first place. And some of my absolute favorite soil profiles that I've seen anywhere in my career have been ones with a change in soil parent material. I just love it. It adds the color, it adds the interesting, the textures, ashy silt loam over gravelly, sandy loam, stuff like that. Really the colors and the rocks. All very beautiful stuff to me. So our bonus geology content, like I previewed before, we are going to take it back to the rock cycle, right, where it all starts. Difference between igneous, metamorphic, sedimentary, it's hopefully all familiar from your maybe grade school science classes or science backgrounds. Rocks begin as magma. When we have magma, lava cooling within Earth's crust, that's how we get our igneous rocks. Metamorphic comes from when those rocks, or any rocks, I suppose, experience some kind of intense heat and pressure that changes the structural makeup, changes the kind of rock we have. We call that metamorphic. It's now changed. And then our sedimentary rocks are kind of the third step in this process, where we have these other rocks that have already formed, begin to erode, they break down, they release their sediments that then can maybe travel somewhere else, consolidate. This could be like bottom of rivers, bottom of the ocean, and actually lithify or create a new rock layer that's a sedimentary rock. And then it's a cycle, of course. So when this happens on the bottom of the ocean, perhaps we have these tectonic plates that are moving around. They're subducting underneath each other back into the Earth's, the mantle of the Earth. This tectonic plate subduction converts these rocks back into magma. Cycle starts again. So those are the rocks themselves, but the actual components of the rocks, like the mineral composition, is going to vary between each stage of this rock cycle. And the important idea here is that there's both primary, secondary minerals. When we have this magma cooling, you're kind of doing this original formation. These elements are ordering themselves, arranging themselves into these mineral, like crystal structures that go on to create the larger rocks. When that happens as magma cools, we call that primary. It's happening like for the first time. But then through this erosion and lithification process, we start to have these secondary minerals produced. So they came out of the Earth's crust, they emerged from magma as a primary mineral, and then over time with weathering, with erosion, we have these secondary minerals created. But as we talk about magma and how that's the start of all rocks, it's important to keep in mind that not all igneous rocks are created equal necessarily. A few different, there's some determining factors that give us different types of igneous rocks. Specifically, what I can think of is the cooling speed and the composition, like the chemical composition, chemistry of the magma itself can give us different rocks. So before we do that, some definitions to add here. I think we talked about this before already with extrusive versus intrusive. When we talk about extrusive rocks, that means the magma cooled outside of Earth's crust, which happened probably pretty fast. Temperature is a lot cooler exposed to the atmosphere compared to in like a magma chamber, for example. So it's really fast cooling that creates really small grain size within the rocks. And intrusive being the opposite means it cooled within Earth's crust over much longer time, cooling proceeded much slower, and we have larger grain size or very coarse grains that you can see individually. So that's our cooling speed. We also have two different magma composition that I want to talk about. The first is called felsic magma or felsic rocks that contain a relatively high amount of silica. I don't need you to remember the exact percentage of this, just that felsic means a lot of silica compared to the other one is mafic, relatively low silica. Intrusive versus extrusive, felsic versus mafic. These four different kind of properties that any igneous rock can have. These definitions are great, but how about some more visual examples? What do they actually look like when they're creating rocks? Well, let's make a little table here. So on the left, let's put extrusive and intrusive. And on the top, we'll do our felsic and our mafic. Starting with one of our intrusive felsic rocks that we talked about in paramaterial lecture, that would be like our granite. Very pretty, great for countertops. The way you have all these different colors, all these different large grains, you can actually see each kind of component of a granite rock specimen. And then our fast cooling mafic, lower silica example that we talked about before was basalt. So if we filled in these other two, then let's think about a mafic rock with low silica content. Felsic versus mafic kind of determines the color of the rock. So if it's mafic, same way basalt is, you'd expect it to be kind of this dark gray, brownish, black color primarily. But now if we're cooling slowly, if instead of erupting or extruding from Earth's crust somehow, like our Columbia River basalts did, maybe some of this magma was just left behind and cooled slowly over time, it's going to have those large grain sizes the same way granite does. So our example rock for this is gabbro. Maybe it's shinier. Maybe you can just see these individual, see these grains that more similar to granite. Unlike basalt, you can see these kind of grains in it. So then similarly, a felsic rock, we would expect it to be kind of similar in color to granites, but if it's fast cooling, it probably doesn't have those same pretty granite countertop grain sizes. An example rock there is rhyolite. Best place to see this is like over in the Cascades on these volcanoes, you have some of this very felsic magma with high silica content. And when a volcano is involved, perhaps that's how this magma was introduced to the atmosphere in order to cool very quickly, have that extrusive cooling, not enough time for these minerals to arrange themselves into large crystals, for example, that we might see in granite. So rhyolite and basalt are the fast cooling ones, very small grain size compared to granite and gabbro, and then our felsic versus mafic determines kind of the color of it. So that's my basic introduction, getting a little more into these silicate minerals specifically. Where are we at? Over here. Getting started here. So these are some of Dr. Strawn's slides. He usually comes in for 2 lectures, couldn't really get the schedules to work out, kind of convenient too. I had him give these while I was gone last year, traveling for the soil judging team, and we had to have an away competition. Now that it's at home, I'm staying right here. And I get to present these mineralogy slides, this mineralogy warm-up, if you will. So we talk about primary and secondary minerals, right, as a little continued review. The primary ones are forming from the magma. For example, this includes minerals like quartz, feldspar, olivine, kind of original form as they emerge from the magma. And then the secondary minerals are the ones that result from erosion or some kind of breakdown of existing minerals. And this is really where clay comes from. Clay in the first place is a secondary mineral, we could say. But then all these iron oxides that give us subordinates, distinctions, these subsurface horizons, carbonates themselves are a secondary mineral. These are just some of the examples that he's going to talk about. As we go through these mineralogy slides, there's going to be a lot of like chemical formulas that go up for like the chemical composition of each one of these minerals. Some of the important ones maybe would be good to know. For example, quartz, the easy one. Just silica, SiO2, silicon dioxide. That's kind of the easy one. And really it's a good one to know because of how common it is. Quartz kind of dominates a lot of our the minerals and a lot of the components of Earth's crust, so much so that if you had to break it down to an element by element basis, the most abundant element in all of Earth's crust, like if we're talking about solid, like the soil and geologic matter, all the solid components of Earth's crust, the most abundant element is oxygen, thanks to this SiO2 oxygen formula. So where you might expect the most oxygen on Earth to be in the atmosphere because it's what we breathe. Actually, that's nitrogen. If you want the most oxygen, it's in the rocks. And then, so he's got a whole list of, I think second place is silica, iron, aluminum, what's next? Calcium. I think this is just the ranking of abundance, but these are just the important minerals from the important elements, I suppose, from the soil science perspective. When we talk about minerals, this is going to be a little bit more of a chemistry perspective too, but how these actual individual elements in these atoms kind of arrange themselves. It can happen in a few different ways, and there's also a few different ways to think about it. So this takes a little bit of imagining. The way that these are all oxygen atoms too, right, as these large kind of circles here. This is one individual mineral structure. So I don't know if you took Soil 205 with Robert recently. Does he talk about this at all?
Crystal lattice.
Crystal lattice structure. Okay, so maybe this is not going to be so new, which puts you guys at an advantage. I mean, I'm doing soil science for a living. I'm not sure if it's any easier to think about it, mineralogy from a like chemistry perspective for me personally as it is for you guys. But the way I think of these kind of crystal structures, they call this like a tetrahedral arrangement in this top row, where you have 4 oxygen atoms per one, silicon in the middle. And the kind of geometry or the way they arrange themselves, it's like a kind of like a pyramid, but it's, if you imagine like 4 basketballs, 3 in like a triangle and 1 stacked up on top of it. So when you're drawing it out, it's got to be in 3 dimensions. All these different like diagrams here are different ways of kind of representing that arrangement here. And then the bottom one, this bottom row is the tetrahedral. No, the octahedral. Tetrahedral is on top. This is octahedral. So you imagine like 4 tennis balls or 4 basketballs, one stacked on top and one stacked on the bottom too, is the way that these oxygen atoms are arranged, and they relate to silica in the middle, usually silicon. Okay, so that's how we kind of represent these minerals, but then all these different mineral forms and different kind of structures or minerals individually that we work with have these different chemical properties. And some of those differences arise when we, of course, when we involve these different elements. And sometimes these oxygen atoms, they create this vacancy in the middle, which can swap out sometimes for different elements. They're usually the positively charged ones, since oxygen itself has a negative charge. So when you're substituting these positively charged ions, we call that cation, or these are the cations, right? That they're positively charged. And in order to fit in this like void space within, in order to fit in this arrangement here between the oxygen atoms, they have to be the same size. The fancy word for this is isomorphic substitution. Isomorphic meaning the same size. Substitution means you're trading out different elements within these mineral structures. When these different elements have different charges, a +3 versus a +2 or something, that might create a permanent like imbalance. So now this part of the mineral has a -1 charge. It's an isomorphic substitution. This stays permanent through the minerals. It becomes just a permanent characteristic of the mineral, and then that's kind of what gives us this cation exchange capacity of soils, the ability to retain nutrients, trade them out with plants, and provide some kind of soil fertility. So the way that all these, so this tetrahedral, this octahedral, these are all like silicate structures. There's, in addition to these two like chemical structures, we have 4 basic ways that these shapes can organize themselves. And we call these these are at least the four silica types of interest. So we have these meso, philo, and tectosilicates. If you can, okay, so now what if I turn this way? What if I do some drawing on the board? Okay, so if I'm drawing in 3 dimensions, 2, 3, 4, this is like the 3 basketballs and then the one on top of it. One of these single arrangements here, one little silicate structure like we have right there on the slide, that itself, you could say, is alone. It's on an island. This would be a mesosilicate, so it has only one by itself. However, when we have a few of these grouped together, right, they share, do they share one or do they share 2? Oxygens. Is it 2? I would like to know. We could have Mary Beth here. She likes minerals a lot more than I do. But we can have them kind of group together like this and start to form a chain. And that would be our enosilicates, a whole long list of these. So pyroxene, amphibole are the chain silicates, or a long list of these. Phyllosilicates, or a sheet of them, you can imagine this continues in both directions and we get a large kind of sheet going. That would be a phyllosilicate. That's why we call it a sheet silicate. And then tecto means it creates like a network of it, if you will, and like a 3-dimensional kind of crystal looking shape. So here's the professional rendering of it. Yeah, so on the very top corner there, a mesosilicate just means one single set of like one little group on its own. Single chain, double chain here, depending on the these element ratios, right? All these groups kind of link together. a two-dimensional sheet for a phyllosilicate. A lot of these clay minerals that like doing ribbon tests, like all these different types of clay, are really just these two-dimensional clay sheets put together, stacked up, and then a three-dimensional structure for the tectosilicate, the more network. So these are some examples. I don't need you to copy this table down. However, they're all primary silicates, the way that these mineral structures are created. And then some of the examples that we're going to go through. So olivine up first is a nesosilicate, just an island. It's only one of these little tetrahedral shapes. For that reason, it's really easily weathered. So it breaks down really quickly. It's not going to last long in soil. We don't have olivine as a major component of the soils in this part of the world, for example. If we find a more recent, a younger kind of soil environment, I've heard of Hawaii as the usual example of like olivine and like sand kind of made of this nesosilicate composition. Might be a green sand beach because of the olivine. Must be beautiful. We'll take Kool-Aid's word. Class field trip maybe one day. However, the reason we don't see green sand beaches everywhere is that it's really easy to break down compared to the other ones because it's just one single structural unit compared to our other kinds of minerals, which have a little more rigid structure to them. So this is a less pretty picture here, I guess. Mineral formulas for the pyroxenes. They get complicated fast, with all these elements and the substitution that's involved. So, right, these are the chains instead of having just one single tetrahedral shape on its own. We've got them all in a single chain for pyroxene, a double chain there, depending on which elements get shared. Our phyllosilicate are clay minerals. This is two different ways to represent it. This is kind of like a top-down view from above, a view from above there, and then a view from the side of the way that all these mineral sheets kind of are arranged with sharing either the basal oxygen, which means like the three basketballs that are on the same level. Apical is the one that's like on the top. For example, some common primary phyllosilicate here, for example, would be mica, anything that creates like a big sheet. So I'm really excited to show some of these off you can see these in the experimental forest. Like if you get into kind of granite paramaterial, it includes muscovite mica or biotite mica. It presents itself as these like sheet minerals, and they're so well organized into sheets that you can peel them apart. Have you guys ever seen like these mica flakes before? You can just, yes, you can bend them. You can just peel them apart if you get your fingernail in there. Yes, they might be thin, kind of film-like. Some of them are so thin you can see through them. So that's like that middle picture is a quarter behind a sheet of muscovite mica, almost transparent. And then the last one is the tectosilicate, our network. So if you just think of quartz or feldspar, anything that makes like this kind of typical crystal shape, it's thanks to the kind of three-dimensional arrangement of these tetrahedral structures. Some of this I feel like is a little too advanced, or I'm going to leave up to Dr. Strawn next week. This is like the feldspar triangle. So rather than sand, silt, and clay, we have different components of feldspar itself. That's what gives rocks like granite kind of different colors is the composition of these feldspar minerals. Kind of a mineral distribution. Oh, here we go. We're felsic and mafic again. So the kind of chemical composition here on a gradient of like temperature of the melting different element concentrations at the bottom, silica content, iron, magnesium, calcium. We can also extrapolate this out to the weathering ability. So we know that olivine itself is not very erosion proof compared to something like feldspar and quartz, which would dominate like granite rocks. Very difficult to weather. High temperature stability equals easier to weather. That's why olivine's all the way on the right. Yep. So then back to our granite, our favorite example, my favorite example. The four different colors you might pick out in granite, especially in this part of the world, are clear, white, black, and kind of pinkish, tannish, maybe. The clear color comes from quartz, those tectosilicates all mixed together. And the black would be like mica flakes or amphibole in this example. And then the pinkish is like the potassium feldspar. Plagioclase feldspar is the other one, usually the kind of white color. So even though granite is, it's our intrusive, it's got these large grains, it takes a relatively long time to weather compared to some of the other rock types. It still weathers. Like we have soil formed from this granite paramaterial up on Moscow Mountain. It's generally sandy, generally contains gravel. However, it takes a long time. We know that Moscow Mountain's pretty old. It's on the about 70 million years is the age of the granite. So over time, as this weathers, eventually we produce clay. So sand and gravel are the first ones, right? They're the most coarse. However, as the years progress, this is 40,000 years, 250,000 years, 60,000 years. It's saying that as weathering progresses, the clay percent is gradually increasing. So we know clay is generally composed of secondary minerals. It takes a long time for these secondary minerals to form. The longer you expose the soil profile to erosive forces in the environment, or just as it ages, you get more clay in general. Okay, anything else I want to talk about mineral abundance? Oh yeah, as particle size decreases from sand to clay, it gets more fine. You go from more primary minerals such as quartz, feldspar, and mica. As they weather, they turn into, the secondary minerals, clays, allophane, oxides, more secondary minerals, generally finer texture. Okay, I think this is where Dr. Strong will pick up next week, the importance of secondary minerals, soil clays. How does the chemistry of these different types of clay affect the soil properties? I will leave that up to the experts. That's all my new content for today. None of that is going to be on the tests today for you guys to worry about. Hopefully it's going to feel a little bit easier. Talking about our favorite soil horizons, soil forming factors, soil processes. I'll be back in our comfort zone. So I'm gonna stop the share. Bring the mouse back. And you guys are good to go. I will see you at 1:30.